Fnirsi sent me this scope for a review, but I found a lot of flaws with it, especially compared to my Rigol, so it was kind of a bad review. They also sent me a bunch of links they wanted to promote, including one for these LCR tweezers, but having just given the scope a bad review, I didn't want to get another freebie, so I paid for these ones myself. They're meant for picking up and measuring tiny little surface mount components, but they work just fine on other components like this capacitor here, 129 microfarads, or this resistor, 39 kilo ohms. So the reason I got these is because I often check the values of resistors before I use them, and it's much easier to just use a multimeter to measure them than to try to decode those little codes on there. But holding those two probes in the multimeter can be awkward, and that's where the tweezers, oh, I gotta put this in capacitance. The probes on here are just kind of awkward to use. So having just the two connectors right next to each other is just so much handier, although it does read a slightly different value. And you can use it on the circuit itself to measure stuff. Although I have a hard time sometimes making contact with the components. I'm not getting this one. There, that's about 10 kilo ohms. And this thing automatically figures out what type of component it's reading, be it a resistor, a condenser, there, 237 nanofarads, or even an inductor. Now I found sometimes, especially for inductors, it guesses it wrong, so you can switch it to manually decide what it's measuring. Let's see what it has to say about this speaker here. And you can hear a beep coming out of the speaker, and that's because this thing sends out a 1 kilohertz sine wave and figures out how a component reacts, and from that decides what it is. And it says this speaker is 18.7 ohms of resistance and 371 microhenry. But this meter, when I measure the speaker, says it's 15 ohms, so that's quite different. But that's because this thing is measuring at 1 kilohertz, whereas this is measuring DC. And I think the issue here is at 1 kilohertz, of course, the speaker's diaphragm moves a little bit. That uses up energy, makes it appear to have more resistance. But on this thing here, I can also change the frequency at which it measures at. So now I just set it to 100 hertz, and we can hardly hear it. And now the resistance is closer to the DC resistance. And it thinks it is a resistor because it doesn't really see that much inductance. I can also change it to measure at 10 kilohertz. Now it sees inductance, and the resistance it thinks is 22 ohms. So especially for inductors, this thing is not quite foolproof because inductors can be tricky to measure. Now if I set this thing to 10 kilohertz and tell it to measure only capacitance, it measures really low. So right now it measures 0.6 picofarads even though there's nothing there. And that's because there's a little bit of capacitance between those probes. So if I grab this thing now and I squeeze the probes together so that they're close to touching, now it says 0.8 picofarads because there's more capacitance with the probes closer together, and almost touching now at 0.9. Now compared to this multimeter, this one reads 0.017 nanofarads with nothing hooked up, or that's about 17 picofarads. But the probe wires themselves already make a big difference, so if I just bunch those together a bit, that more than doubles because now I have effectively some capacitance between the wires being close together. So this, without any probes, can go a lot lower. So I picked out a series of condensers and capacitors to test this with. Let's measure every one. With this 15,000 microfarad capacitor, it doesn't always recognize it as a capacitor, so it just says 6.5 milliohms. Now it says 27 millifarads, which would be about 27,000 microfarads. So I'll write that down. So that's clearly not right, but let's change the measurement frequency to 100 hertz because this is not exactly a surface mount component. And now we have 21.1 millifarads, so that's 21,000 microfarads, which is not terribly close, but it gets you the idea. Let's check this one again. Come on. 39.8 microfarads, so pretty close. So the 100 hertz was only really necessary for this to get even close. I just remeasured all those caps with this meter, which I trust a fair amount and then worked out the differences, and it's within a couple of percent for most of these, although for the electrolytics it's no longer close, especially for this one, the 15,000 microfarad capacitor, but this is not exactly a surface mount component, although I suppose I can pick it up with it. Whoops. I also saw a significant difference with the 47 picofarad condenser. So the tweezers read 48.8 and the multimeter read 60, but I can't really trust the multimeters for capacitances that low, so I think this one probably got it right. Next I got a whole bunch of resistors, and these two multimeters agree almost exactly on those ones, so I'm pretty confident those are right. So let's try all these with the tweezers. So for the mid-range, these tweezers were really close with only a minor error here. For 20 megohms, it actually read it as an open circuit and only showed it in small that there was a resistance, and the 10 megohms is off a little bit. Now at the low end, it's also off a little bit, so a 1 ohm resistor read at 921 milliohms, so that's off by 8%, and the 0.1 ohm, it read at 69 milliohms, that's off by 31%. Mind you, the other meters couldn't read the 0.1 ohm resistor either because they only go to 0.1 increments. So in some ways, this one actually did better than the multimeters. Now these tweezers can measure inductances, but I don't have an inductance meter to check the measurements against. But if I connect an inductor and a condenser together, that forms a resonant circuit like this, and the frequency of oscillation is determined by this formula as a function of inductance and capacitance. So now I've got my scope hooked up to this, plus a couple of extra wires, so I can electrically give it a kick with a little battery. So you can see a waveform pop up on here. I'll just change the trigger so it only triggers once. There we go. So I'll just put some cursors on this and I'll measure 2 periods of this waveform. So that's 2 cycles right there. And it says the frequency is 5.34 kilohertz, but we know it's actually twice that because we've got 2 cycles. So now I can measure the inductance and capacitance of my components individually and then plug those into my formula. Now I have to put those in as whole henries and whole farads for the units to work out, and from that I can work out what the frequency of oscillation should be. My calculated frequency is 10.385 kilohertz, and measured was 10.62. That's a 2.3% difference in frequency, but because there's a square root here, I could have as much as a 4.5% difference in the inductance to get that kind of error in frequency. And I repeated this procedure with a whole range of inductors and appropriate condensers to go with them. And on the whole, they came out pretty close. The 0.6 microhenries is a bit on the low end extreme, and that came out 20% off. And then down here, this solenoid and this crossbar switch magnet have inductance of 1/4 Henry and 1.7 Henries, and those came out a fair bit off too, but you'd never see inductances like that in an actual circuit. So for the most part, it's not bad. Now this thing is actually meant to be used with surface mount components, so I heated up this circuit board with a heat gun and then picked some of the components off with these tweezers because I didn't want to get these ones hot. And then I tried to measure some of these components with the tweezers. Oops. Ugh. Ah. Ah. So the way these ends go on here, they don't always meet because they have a bit of wiggle room, so they need to be aligned with each other and then the knobs tighten up. And I'm not always making contact, probably because of conformal coating on this thing. Oh, gone. Not making contact again. Oh, gone. So I never had this problem with these conventional tweezers. The components didn't go flying, but with this, the points are just too polished and smooth and slippery. And so when I squeeze on the component, oftentimes it just ends up snapping out and goes flying, and it's gone. Now the tweezers come with an extra set of points, so I took that other set of points, flipped them inside out, and roughened them a little bit with sandpaper, and then put those on. And with that slight modification, it doesn't shoot the components across the room quite as often. But fundamentally, these just aren't stiff enough because if I squeeze them together like this, I can make the points go this way or that way with not very much force because they're just not stiff enough. So as tweezers for surface mount components, they're just terrible. And I've played around with these quite a lot since I got them over a few days, and just now the battery is low, so battery life is pretty good. And now I'm going to sort these condensers back in the box, and these things are just so handy for that. And looking online, there's other tweezers like this available, though none of them cheaper, and this one has more capability than most of them, although I suspect some of the other tweezers are actually better at being tweezers. And I was able to get an affiliate link for these, at which point I am very much biased towards recommending them, just don't use them for surface mount work.